In the stream of wireless communication, did you ever thought how a communication is established between two devices which are far away from each other? Or if I say how transmission and receiving occurs in satellite in terms of satellite communication? Well, today we are going to discuss about this topic which is generally known as free space propagation model. By using this model, we are able to predict the receiver power decays as function with a large separation distance. This model is originally developed on the path loss of a line of sight communication. But a very basic question arises, why in terms of a model? Well, it is used as a model because several parameters are used to calculate the LOS path in a free space environment. Any object that creates absorption, diffraction, reflections, or any other characteristics can alter the phenomenon of a radiated wave. It is valid in a far-field region from the transmitting antenna and based on the inverse square law of distance, which states that the received power at a particular distance from the transmitter decays by a factor of square of the distance. The Friis equation for received power is calculated as PR of D is equal to PT GR lambda square by 4 pi D whole square multiplied by L, where PRD is received signal power in watts. D is the distance between transmitter and the receiver in meters. PT is the transmitted power in watts. GT is the transmitter gain and GR is the receiver gain, and lambda is the wavelength in meters. L is the system losses. The gain of an antenna is reflected to its effective aperture, that is SE, which can be calculated by G is equal to 4 pi AE by lambda square. Also, the effective aperture AE is related to the physical size of the antenna, and lambda is related to the carrier frequency by lambda, that is equal to C by F, that is equal to 2 pi C by omega C, where F is the carrier frequency, omega C is the carrier frequency in radians per second, and C is the speed of light. The free space model is only a valid prediction for PR for values of D, which are in far field from the transmitting antenna. This far field region is generally known as the Fraunhofer region of a transmitting antenna. The Fraunhofer distance is given by D of F, that is equal to 2D square by lambda, where D is the largest physical linear dimension of the antenna. Additionally, to be in far field region, DF must satisfy DF, that is very greater than lambda. Till now, we have understood these equations, and practically it is clear that it cannot hold the condition for D is equal to 0. For this reason, large-scale propagation model used a close in distance D0 as a known received power reference point. The reference distance must be chosen that it lies in the far field region, that is D0, that is greater than equal to D of F, and DO is chosen to be smaller than any practical distance used in mobile communication system. Thus, the received power in free space at a distance greater than D0 is given by PR of D, that is equal to PR of D0 multiplied by D0 by D whole square, where D is greater than equal to D0 is greater than equal to DF. In mobile radio systems, it is not uncommon to find that PR may change by many orders of magnitude over a typical coverage area of several square kilometers due to the large dynamic range of received power signals. Often, dBm or dBW units are used to express the received power levels. In a simple approach, it can be represented by taking the logarithm on both sides multiplied by 10. For example, if PR is in units of dBm, the received power is given by PRD in dBm, that is equal to 10 log PR D0 by 0.001 W plus 20 log of D0 by D, where D is greater than equal to D0 and D0 is greater than equal to DF. So today we have learned introduction to free space propagation model, development and line of sight communication, free space equation for received power calculations and other parameters, and Fraunhofer region and calculation with Friis equation, and practical distance measuring and conversion of received power in dB. We will meet again with another interesting topic of this session. Till then, keep watching and keep learning. Bye.